All right, so today we are going to go through some problems where we're going to be working circuits in the frequency domain. So this will be steady state sinusoidal circuit analysis. And this is the circuit that I want to analyze first. So I'm going to have some sinusoidal voltage source Vs of t. Here, let's put some resistance. Let's say that this is going to be 10 ohms. This will be a current source. Let's make this an inductor, actually. 2 henries. And here will be some capacitance. Let's make this guy a third of a farad. And finally, let's put that in parallel with another resistor, which will look like 5 ohms. The voltage Vs of t will be 12 cosine 2t plus 21 degrees. And the current Is of t will be 1/2 2t minus 31 degrees amps. And let's see, I want us to find this voltage and this current. All right, so I believe at the end of the last class meeting, I asked you guys what you felt like you needed review on. A couple of people said current division. I also said that we might take a crack at source transformations and superposition and all of that kind of stuff. So we're going to see what different ways we can come up with to analyze this particular circuit to kind of highlight some of those techniques. So the first way, or actually, the first thing before we decide on any analysis technique whatsoever is we want to convert the circuit from the time domain into the frequency domain, right? So we're going to do that just like we did with the problem at the end of our last class meeting. We are going to convert all of our voltages and currents into phasor representations, and then we are going to convert all of our resistors, capacitors, and inductors into their impedance representation, right? So if this is our time domain circuit, then in the frequency domain, it should look something like this. So this is going to be my phasor source voltage. This will be the impedance of the resistor, which we'll put in a moment. Here's my phasor source current. The impedance of my inductance. The impedance of my capacitance. And finally, the impedance of my other resistance. So let's start with our voltage source first. What should the phasor representation of Vs of t be? Patrick? 12 angle 21, absolutely. So we kept the magnitude, kept the phase angle, and threw the rest away because we have a cosine function, so we don't have to do any real work there. So 12 angle 21 degrees volts. And somebody else tell me what the phasor representation of my current should be. 1/2 angle negative 31, all right? I'm gonna put the amp down here because I didn't give myself enough room. Okay, so we have our source voltages and currents converted into a phasor representation. Now, just for the sake of argument, I'm gonna go ahead and put a phasor current IY here and a phasor voltage Vx here, so that literally all of our time domain currents and voltages have been represented by a phasor equivalent. So now we're going to move along to our impedances. Okay. So the impedance of a resistor is just the resistor value itself, which means my 10 ohm resistor continues to look like a 10 ohm resistor, and my 5 ohm resistor continues to look like a 5 ohm resistor. Where we're actually going to have to do something is with our inductors and capacitors. So the impedance of an inductor, just to remind you guys, is simply J times omega times the inductor value itself. So who can tell me what omega is for this circuit? Just for the sake of argument, humor me and use units. 2 radians per second, thank you. All right, so we have 2 radians per second times 2 henries, where a henry is a volt second per ampere. That all comes out to look like 2 times 2 is equal to 4 ohms, and then there's that J. So we've got a J4 ohm impedance here for our inductor. And then we have our capacitor, where the impedance of a capacitor is given by 1 over J omega C, which is the exact same thing as negative J over omega C. Since omega is 2 radians per second and C is 1/3 of a farad, we're going to have 1 over 2/3, which is going to look like 1.5, and then we have that negative J. So if my mental math is correct, this should look like negative J 1.5 ohms. Just to make sure I'm not screwing anything up, I'm actually going to put that one in my calculator. Yep. All right. So we have completely transformed our circuit from the time domain into the frequency domain, which means we now no longer have to worry about terrifying trig. We just have simple algebraic relationships like we had in our DC circuits. So there are several different ways that we could approach this problem to figure out the 2 quantities of interest here. I'm going to start by using superposition. And as part of this superposition, we'll wind up using a couple of other things as well. So using superposition, it's been a minute since we've done this. That's that technique that we learned where we have one source on with all of the other sources off, analyze the circuit, then have another source on, all of the other sources off, analyze the circuit, and then we repeat that over and over and over again for however many sources there are, and we just combine the results at the end. Okay. So let's start with our voltage source on and our current source off. So our circuit would look like this. 12 angle 21 degrees volts in series with a 10 ohm resistor in series with a J4 ohm inductance. Here's our minus J 1.5 ohm capacitance. Then there's our 5 ohm resistance. I'm going to call this current IY prime, and I'm going to call this voltage Vx prime. So let me ask you guys a question. Do you want me to tell you how I would do things, or do you want to actively participate in this? Actively participate. All right. So let's actively participate. How can we solve for the voltage Vx here? Absolutely right. So let's do voltage division. So Vx prime is going to look like 12 angle 21 degrees volts. In my numerator, I'm going to have the total impedance I'm finding the voltage drop over, which Patrick suggested was 5 ohms in parallel with minus J 1.5 ohms. I agree with that. So that's going to look like 5 times minus J 1.5 divided by 5 minus J 1.5. Then in my denominator, I'm going to treat that resistor in series with an inductor like a single impedance of 10 plus J4 ohms. And now I'm going to have that same parallel combination of impedances on the right-hand side. So that's going to look like 5 times minus J 1.5 over 5 minus J 1.5. And we now have something that we should be able to throw into our calculator. So let's do just that, right? So 12 angle 21 times what I have stored in my calculator is X over 10 plus 4I plus X. I got 1.606 with an angle of negative 66.444 degrees volts. That's the polar representation as a rectangular form complex number. This looks like 0.642 minus J 1.472. So before we move along from here, did anybody else get a different number? So just as a heads up, when dealing with voltages and currents in particular, I will practically always use a polar form representation, okay? So on your exams and things like that, not going to see an available option of a rectangular form complex number. It'll always be a polar form, okay? All right, so this was Vx prime. Nobody's really expressing any opposition to this, how would we solve for IY prime? So what was the other thing I heard, Brandon? So which voltage are you referring to specifically? The voltage Vx prime or the 12 angle 21? Okay, so I thought you said the top of the big fraction. Okay, I got you. Yeah, so effectively we could use Ohm's law. So that would be 12 angle 21 degrees over the denominator of that large, or the denominator in our voltage division thing. We could also just take Vx and divide by the 5 in parallel with minus J 1.5. That'll give us the exact same result, because the same current is flowing through this single loop circuit effectively if we treat those two impedances in parallel. So realistically, the easiest way to do things here is going to be Ohm's law, right? So let's use the suggestion from Brandon. So we have 12 angle 21 degrees volts divided by 10 plus J4 ohms plus 5 in parallel with minus J 1.5 ohms. So throwing that into my calculator really quickly, I got 1.117. Missed a one in there. With an angle of 6.857 degrees. And in rectangular form, that looks like 1.109 plus J 0.133. Anybody else get a similar result? Good deal. All right, so we've solved for Vx prime and Iy prime, and at this point we have used voltage division and Ohm's law here in the frequency domain, and the rules for using them are exactly the same as they were way back when we were analyzing DC circuits. One thing that I want to impart to you guys is by working circuits in the frequency domain, we're not expected to do literally anything new whatsoever. This is just review. All right, so unless anybody has any questions about this, we can move on to current source on, voltage source off. Everybody seems to be opposed to things. All right, so voltage source off, current source on. Our voltage source on the left-hand side is going to now look like a short circuit. Here's our 10 ohm resistor. Here's our current source, which was 1/2 angle negative 31 degrees amps, if memory serves me correctly. If it doesn't, please tell me. J4 ohms. Minus J 1.5. Five ohms here. Here's our current IY double prime. Here's our voltage, VX double prime. So how might we solve for one of these quantities? So we definitely could do a source transformation because the phasor current source is in parallel with that 10 ohm resistor, which that would allow us to calculate the voltage VX double prime by using voltage division, much like we did in the previous example. So that seems like a reasonable thing to do. So what's my source transformation going to look like, right? How do I do a source transformation? Anybody remember? Okay. Alrighty, absolutely correct. So what should 1/2 angle negative 31 degrees amps multiplied by 10 ohms look like? The fact that you're using a calculator terrifies me. 5 angle negative 31 degrees, because we learned that resistance does not change the phase angle at all, right? So it's literally just multiply the magnitude by a factor of 10 and then keep the phase angle the same because we're dealing with a resistance. Picking on you a little bit, but also serious. 5 angle negative 31 degrees volts in series with 10 ohms, J4 ohms, minus J 1.5 ohms, five ohms. And here is the VX double prime that we're looking for. So let's just apply voltage division much like we did a moment ago. VX double prime is going to be 5 angle negative 31 degrees volts times 5 ohms times minus J 1.5 ohms over 5 minus J 1.5 ohms. And then down here, we're going to have the 10 plus J4. And then that same parallel combination. So let me throw this into my calculator if it'll turn on. I got 0.669 with an angle of negative 118.444 degrees. Volts in polar form and negative 0.319 minus J 0.588 volts in rectangular form. Before we move along, anybody confirm that this is correct? Alrighty. So how might we solve for IY double prime?
So I have a
Mhm.
why didn't you put the squiggly on the voltage source? Is that only commonly in AC?
I'm lazy. Doesn't matter. I can put it there. I'm just lazy and forget. So IY double prime. Ohm's law. So I am not sure that that's going to work. Let's try. Okay. So Brennan, what I think you're suggesting is that this current right here is IY double prime. Now, the reason why I'm not sure if this is going to work is because we performed a transformation. So we moved things, and moving things tends to have repercussions. Okay. So we'll work this, see what we get, and then we'll work and find IY double prime using our original circuit. And I'm 70% sure that the answers are not going to be the same. I'm willing to admit that I might be wrong, but I don't think I am. So let's see what shakes out, right? So maybe IY double prime would be equal to 5 angle negative 31 degrees volts divided by 10 plus J4 ohms plus, I'm getting tired of writing this thing down over and over again since we've used it so many times. So I'm just going to put 5 ohms in parallel with minus J 1.5 ohms, and we all know what that means. Okay. So I got 0.466 with an angle of negative 45.143 degrees amps. And I'm going to leave it like that because I'm not going to bother writing it out in rectangular form since I'm not sure it's correct. So that's a maybe. And again, the reason why I'm suspicious that this is going to work is because we moved that circuit element. It doesn't look like we moved it because it's still in that same position, but it is connected to a different network than it was before, which means the current flowing through it's probably going to change, okay? So how might we solve for IY double prime looking at this top representation? Current division. So IY double prime is going to look like negative 1/2 angle negative 31 degrees amps. And then I'm going to have 1 over 10 ohms up here in the numerator. And then I'll have 1 over 10 ohms plus 1 over, so this is going to be J4 plus that 5 in parallel with that minus J 1.5, right? So this guy right here represents all of the impedance to the right of the current source. So that I see 2 impedances in parallel with my current source, which is what allows me to apply current division. Okay. So throwing this into my calculator, I'm going to have negative 0.5 angle negative 31, 1 over 10, 1 over 10, plus 1 over 4i plus x. and I got 0.124 with an angle of negative 144.085. Or in rectangular form, negative there's going to be 0.100 minus J 0.073.
Why did mine give me 35? I have the same, wait, no, I didn't.
Did you put the negative out front? So let's talk about why that negative is out front for one thing. Anybody have any thoughts as to why there's a negative in front of our current division? Because it's correct. Exactly correct, Colin. So realistically, or normally, we would expect current flowing up would split and flow out like that. Because IY double prime is defined in the opposite direction, our current division relationship needs to have a negative sign to account for that change in direction. 100%. So, Brennan, did we get the same result? Absolutely not. So, I'm not saying that it will always work out this way, but particularly with a current, it's going to be rough sailing. So anytime that we make a change to a circuit like that, we have to be aware of whether or not we're changing a fundamental relationship for one of the quantities that we are solving for, okay? If it had been a voltage, it would still just be the voltage between 2 points in the circuit. And those 2 points would be the same, but a current is a bit more hard to deal with. So I was actually very glad that somebody suggested source transformation because I was hoping to trap somebody. So you played right into my hands. Awesome. Okay, so we've analyzed the circuit with the voltage source on, current source off. We've then analyzed the circuit with the current source on, voltage source off. What do we do now to get our final answer? Add them together, okay? So we could say that Vx is simply Vx prime plus Vx double prime, and I did not have the forethought to save any of these things in my calculator, so we're going to introduce a little bit of rounding error here, but it'll be okay. So if I scroll up here to Vx prime, I had 1.606 with an angle of negative 66.444. To that, I'm going to add 0.669 with an angle of negative 118.444. And the result is 2.086 with an angle of negative 81.086 degrees. And IY is just going to be IY prime plus IY double prime. So let me scroll up here. 1.117 with an angle of 6.857 plus 0.124 with an angle of negative 144.085, which I get to be 1.010 with an angle of 3.440 degrees amps. Are we done? I disagree. Go way back to the beginning. Our goal was to solve for Vx as a function of time and Iy as a function of time. So just because we're done in the frequency domain doesn't mean we're done with the problem. Our last step is simply to convert back from these phasor voltages and currents into a time domain voltage and current. We do that by keeping the magnitude, keeping the phase angle, and adding the cosine 2t bit back in. Okay. So Vx of t is just going to be 2.086 cosine 2t minus 81.086 degrees volts. And Iy of t is going to be 1.010 cosine 2t plus 3.440 degrees amps. So we practiced superposition, Ohm's law, voltage division, and current division, all by looking at that. Okay. So, oh, and a source transformation. Thank you, Ashton. So we reviewed literally everything we wanted to review in that one problem. So what I want to do now is show you guys how I would actually work it, which is probably a bit easier. This is not going to always work, but for relatively simple circuits, I'm going to make a copy of our original frequency domain representation here. I'm going to call this method 2. Nodal analysis. Okay. And I put nodal in quotation mark there because this isn't really nodal analysis at all. It's just Kirchhoff's current law. I'm just making a point to choose a ground to make my life easier, which is why I'm going to call it nodal. Okay. Now I told you guys that we can't solve a system of equations in our calculator that has complex numbers in it. So we are not going to. We are going to wind up getting a single equation, single unknown system that we can solve just using good old algebra. And then use the results of that to get the quantities that we want. Okay. So I'm going to put ground here. And I'm going to solve for this nodal voltage, which I'm going to call VC. So if I apply Kirchhoff's current law at node Z, what I'm going to have is VZ minus 12 angle 21 degrees volts divided by 10 ohms minus IS, so 1/2 angle negative 31 degrees amps plus VZ over, and I'm going to lump all of that stuff to the right as a single impedance. So the key to this technique is realizing that there's a way to make it look like there's only one unknown voltage in the entire system, right? So this is gonna look like J4 plus 5 in parallel with minus J1.5. And set this equal to 0, right? So the only unknown voltage in this system, if I lump all those impedances together on the right-hand side, is the nodal voltage VZ. So now I'm just going to move stuff around, right? So I could say that I have VZ multiplied by a factor of 1 over 10 plus 1 over J4 plus 5 angle, that's going to be in parallel with minus J1.5. And so I've got my variable and its coefficient on the left-hand side of the equal sign. And now I'm just going to move all of the constant terms to the right-hand side of the equal sign, which is going to look like 12 angle 21 degrees volts divided by 10 ohms plus 1/2 angle negative 31 degrees amps. Now, I'm going to call this thing here lowercase a, just because that's what I'm storing into my calculator as. And this thing over here is going to be lowercase b, just because that's what I'm storing in my calculator. And it should be fairly obvious that VZ is just going to be B over A. So I'm going to take a moment to do that. So when I did this, I got 3.855 angle 73.271 degrees volts. Storing that as C, just as a note here. So before we move on from here, did anybody else get something similar?
So I get these folks.
I'm almost positive it doesn't, but you can give it a whirl. All right, so assuming, and I'm not really making an assumption here because I feel like I did it correctly, that this is VZ. Now let's talk about how we could solve for the quantity Vx and Iy. Let's look back at our equation here, okay, or our circuit here. So I could find Vx just by doing voltage division once I know what VZ is, okay? So Vx should just be VZ times that 5 in parallel with minus J1.5 over J4 plus that 5 in parallel with minus J1.5. So I'm going to throw that in my calculator. So what I have stored as C times what I have stored as X over 4I plus X. Now I got 2.085 with an angle of negative 81.088. volts. Let's scroll up really quickly. Yes. So I'm choosing to represent that bottom node as ground, but I could get the exact same result just by doing KVL equations all over the place. This is just a quicker way to get to the same thing. So I don't understand your question, or maybe I missed it. Okay. So we just got 2.085 with an angle of negative 81.088. Let's scroll up here. 2.086 with an angle of negative 81.086, but there was rounding error introduced because I didn't store things in my calculator. We got the exact same result, but in my opinion, way faster, right? How would we solve for that current IY? Well, that's just VS minus VZ over 10 ohms. Right? So VS was 12 angle 21 minus what I have stored in my calculator as C divided by 10. 1.011 with an angle of 3.451 degrees amps. How does this compare to what we got previously? Again, pretty darn close, just a little bit of rounding error there. Just something to consider. If you can get a circuit to look like it only has one unknown voltage, you can use that pretty quickly to burn through a lot of the stuff that I could possibly throw at you. Okay. If you can't, then it's KVL, KCL, Ohm's law, voltage division, current division, superposition, source transformations, all of that kind of good stuff. Realistically, though, it's just whatever you feel comfortable with is what you should be using. So I can either let you guys work on your ICA for an hour, or we can work another problem. I'll just pull one from the book. What do you want? Do you want to do stuff, or do you want me to do more stuff? Use your words. ICA. Okay, ICA it is. I'll be here to answer questions if you have any.